Welcome to Unit 11 of this course. In this unit, we will be looking at a data structure for representing transition systems. And the name of this data structure is going to be binary decision diagrams, BDDs in short. In the first module, I will give you an introduction to BDDs. A short recap of what we have seen in this course. Model checking is essentially modeling systems as finite state machines and modeling requirements in a formal language and using automatic tools to check properties against these finite state machines. So in our course, we have been looking at transition systems. These are diagrams with states and transitions. We have seen what kind of properties can be checked on transition systems. In particular, we have been looking at LTL and CTL properties. We have also seen the tool NewSMV that can read transition systems in a format of this tool, and we can also write LTL and CTL properties, and NewSMV can automatically check these properties on the transition system specified. In the last unit, we had seen that when we have multiple modules in NewSMV, the number of states in the transition system increase exponentially. If you have one Boolean variable, there are 2 states. If you have 2 Boolean variables, there are 4 states. If you have n Boolean variables, there are 2 parent states, and so on. Clearly, we need an efficient way to represent transition systems since they are huge. In this unit, we will look at a data structure for representing transition systems efficiently. In this module, I will introduce you to this data structure called binary decision diagrams. In module 2, we will see some operations that can be done on BDDs. We will see algorithms for operations on BDDs. And in module 3, I will explain how BDDs can be used to represent transition systems. This unit, the reference would be the book Logic in Computer Science, 2nd edition by Huth and Ryan, sections 6.1 to 6.3. Let's start with what are called Boolean functions. During the course of the unit, we will understand why we are talking about Boolean functions. So what are Boolean variables? These are variables that can take values 0 or 1. In other words, false or true. Suppose x and y are Boolean variables. F of xy, a function given by x plus y, is a Boolean function. Now this plus is a Boolean addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 would still be 1. So this is the logical OR. So if you look at it as false and false, if you have false or false, it's going to be false. False or true will be true. True or false will be true, and true or true will be true. And this is the truth table corresponding to this Boolean function. When x and y are 0, f of xy is 0. 0 and 1 will be 1. 1 and 0 will be 1, and 1 and 1 would be 1. So this is the standard truth table for the logical OR. Now let me give you an example of one more Boolean function. A Boolean function takes as input some Boolean variables and outputs either 0 or 1 for each combination of inputs. So This is a function defined as f of xy equal to x dot y. Now what is this dot operation on Boolean variables? 0 dot 0 is defined to be 0, 0 dot 1 is 0, 1 dot 0 is defined to be 0, and 1 dot 1 is defined to be 1. So what is your guess? What is this dot? It's nothing but the logical AND. And here is the truth table corresponding to the AND. Now let me define yet another operation on Boolean variables. F of x equal to x bar is another Boolean function. Now how do we define this bar operation? 0 bar is defined to be 1 and 1 bar is defined to be 0. So this is just the logical NOT. And here is the truth table representation of this Boolean function. In general, if you have n Boolean variables, a Boolean function is just a function that takes a valuation of x1 to xn and maps it to either 0 or 1. It's a map from some valuation of x1 to xn to 0 or 1, and you can define Boolean functions using these basic Boolean operations plus dot and bar. For example, this is a function x bar plus y. So this is a function over 3 variables. It says x dot y plus y bar dot z. So this is formed out of these operations. Similarly, f3 of xyz is x plus y bar dot z, the whole thing bar. So we have seen what Boolean functions are so far. Let us now see how to represent Boolean functions. So far it's simple. So here is a Boolean function. F of xyz is x dot y plus y bar dot z. Now you can represent it using a truth table. So this column is for x, this column is for y, this column is for z, and this is for f. Now if x is 0 and y is 0, x dot y is 0. Now what about y bar dot z? Since z is 0, y bar dot z is going to be 0 as well, and 0 plus 0 will be 0. Let us see one more. X dot y 0 dot 0 will be 0 plus y bar dot z will be 1 dot 1, which will be 1. So this value is 1. Similarly, you can check for the other entries. So this is called a truth table for this Boolean function. You just map each valuation to the corresponding value which f associates it with. There's another way of looking at this truth table. This is called the binary decision tree. So the nodes are x, y and z. So this is the root node x. This dashed line says that the value associated to x is 0. The thick line says that the value associated to x is 1. Similarly, here at y, the dashed line says that the value associated to y is 0. The thick line says that the value associated to y is 1. So this path is 0, 0, 0. And for 0, 0, 0, f is 0. Now what is this path? 0 for x, 0 for y, and 1 for z. So 0, 0, 1 is 1. Now 0, 1, 0 is 0, and so it's 0 here. 0, 1, 1 is 0 again. So 0, 1, 1 is 0 again. Now what about this? 1, 0, 0 is 0. 1 0 1 is 1, 1 1 0 is 1, and 1 1 1 is 1. So this is just another representation of the truth table in the form of a tree. Each path corresponds to an entry here. Okay, so these two are equivalent representations for this Boolean function. What are the operations that you can do on truth tables? We know operations that can be done on functions: plus, dot, and the bar. Now, since we are representing Boolean functions using truth tables, we should be able to do these operations on truth tables as well. Let us see how to do it. So consider this Boolean function, which is the f of xyz that we saw, the complement of it. So that is x dot y plus y bar z whole bar. Now this is the truth table for f. How do we get the truth table for g? You look at the corresponding entry in f and just take the complement. If it is 0, put it to be 1. If it is 1 here, put it to be 0. 0 here, put it to be 1. 0 here, put it to be 1. 0 here, put it to be 1. Now these three are 1, so here you will get 0, 0, 0. So given the truth table of f, you can compute the truth table of f bar by just swapping the values in this column. So this is a simple concept. How about doing a plus? So this is a truth table for f. This is the truth table for the function g. Now we define h to be this plus this. Now how will the truth table of h look like? You look at the corresponding values in this one and in this one and just do a plus. So 0 plus 1 will be 1. 1 plus 1 would be 1 again. 0 plus 0, 0. 0 plus 0, 0. Since here everything is 0, we just copy this truth table here. Yes. So what you did, you systematically went through each entry and the corresponding entry here and then filled it by doing a plus here as well as, by doing a plus of this and this. This is how you do plus of two truth tables. Similarly, how do you do a dot? You look at corresponding entries and instead of doing a plus, you just do a dot. So 0 dot 0 is 0, 1 dot 0 will be 0 and so on. So wherever there is 0, you will get 0, 0, 0. And here the last three are ones and ones you will get 1, 1, 1. What do you need to observe? If you are representing Boolean functions using truth tables, what is the space required? If there are n variables, note that there are 2 power n rows and each row has n plus 1 bits. So here there were 3 variables, so there were 8 rows and each row had 4 bits. So for n variables, the truth table needs to store 2 power n dot n plus 1 bits. And for computing operations, you need to visit each entry of the truth table. So if you have n variables, you need to look at 2 power n values. Note that sequential circuits can be modeled using Boolean functions. Sequential circuits are gates with possible feedback and they can be modeled using Boolean functions. And a circuit with 100 variables will need more than 2 power 100 bits. Okay, and 2 power 100 is a huge number. Clearly, we need a better way of representing Boolean functions. And this is what we are going to see next, an efficient representation for Boolean formulas. So consider the Boolean formula x bar dot y bar. This is the binary decision tree representation. This is equivalent to the truth table. 0, 0 goes to 1 because x bar dot y bar, 0 bar is 1 and y bar is, 0 bar is 1 again. So 1 bar dot 1 dot 1 will be 1. 0, 1 will go to 0. 1, 0 will go to 0 and 1, 1 will go to 0 again. Fine. Can we represent this in a better way? Firstly, there is no point of having 3 zeros. It's enough if we have one representation for the bit 1 and one representation for the bit 0. Now here, this y, both its successor edges go to the same node. If you notice, this decision point, see, this is a decision node, right? At this node, if you choose to take 1, you go here. If you choose to take 0, you go to the same node. Here, if you choose to take 0, you go here. If you choose to take 1, you go here. Clearly, this decision is unnecessary. What can you do? You can just remove this node and say that whenever x is 1, the value will be 0 no matter what y is. This says that if x is 0, then depending on whether y is 0 or 1, there are differences. But however, when x is 1, we don't care what y is. The value assigned will always be 0. So this is a more efficient way of representing it because we have lesser space. This kind of a diagram is called a binary decision diagram. Let's see some more examples. Look at this binary decision tree. Let's see if we can make it smaller. First step, reduce all zeros to 1, 0 and all ones to 1, 1. Just keep one leaf 0 and one leaf 1. Now this z, its 0 child goes to 0 and its right, the 1 child goes to 1. Look at this, both of them go to 0. So both its edges go to 0. Here the dashed edge goes to 0 and the thick edge, so the dashed edge represents the decision point that z is assigned 0. It goes to 0 and this thick edge goes to 1. Now what about this thing? Both of them go to 1. So when you reduce the leaves to this situation, this is how the edges will look like. Now clearly this decision point and this decision point are unnecessary. Once you come to this y and you say that when you take 1, you have to go to 0. Similarly from here, if you take 1, you have to go to 1. So you can remove this z and this z. You are left with this z and this z, but note that the subtrees are isomorphic in the sense, look at this node z and this node z. Its dashed edge goes to 0 and the thick edge goes to 1. Here again its dashed edge goes to 0 and its thick edge goes to 1. So these two are identical. So why do we need to have two representations for them? Instead, we can just keep one representation for this particular tree. And what do we get? We get one representation here and y's dashed edge goes to this z. Similarly, this y's dashed edge goes here and the rest are same. So this one's dashed edge goes here and the thick edge goes here, and this one's one edge, so I can also call it the one edge, this goes to 0. Similar to this, we just copy it. Now this uses lesser nodes than this one, and this is a binary decision diagram. So these kind of diagrams are called binary decision diagrams. Note that these two are called reduced BDDs. BDD is for binary decision diagrams. So look at this. This has the potential to be further reduced because this is an unnecessary node. Similarly, this is an unnecessary node. After doing the reductions, we got this. This cannot be reduced further. See, this y is different from this y because its one edge goes to 0. Here its one edge goes to 1. So you cannot say that these two are identical. Okay, so here we cannot merge any nodes. So these are reduced BDDs. Similarly, this is again a reduced BDD. In general, such diagrams are called BDDs. Now we informally saw how to reduce. Let me give you the reduction rules. The rule C1 says we can remove duplicate leaves. If we have multiple 0 leaves and multiple 0 ones, we just make it to be one leaf for 0 and one leaf for 1. Removal of redundant tests. We were removing these unnecessary decision points. And C3, removal of duplicate subtrees. If there are two subtrees which are identical, we can just keep one representation for it. Let's go through the examples. So what did we do first? We applied the C1 rule to get one representation for the leaf and one representation for 1. I mean, one representation for 0 and one representation for 1. On this, we applied C2. See, there are redundant tests. This Z and this Z have redundant tests. So by applying C2, we removed these Z's. So from this Y, we went directly to 1. And from this Y on a 1, we went directly to 0. And then we applied C3 to remove duplicate subtrees. We just kept one subtree to represent these two which were identical. So after applying these rules, we get the reduced BDD. Similarly here, we applied C1 first to get one representative for the leaves, and then we just had to apply C2. We could not reduce this any further. So this was a reduced BDD. So that is the introduction to this simple concept called BDDs. What do we want? We want to represent Boolean functions. A standard way of doing this is to use truth tables. However, we can do better by making use of these BDDs. We have seen some examples, and then there are ways of reducing these BDDs using the rules that we saw. C1, C2, C3. They are very intuitive rules. Finally, they represent the same Boolean function, the same truth table. For example, here this says that on an x, if x is 1, no matter what y is, the value assigned is 0. Similarly here, it says that when x is 1 and y is 1, no matter what z is, we get 1. If x is 0 and y is 1, no matter what z is, we get 0. Okay? So this is an introduction to BDDs. We will see in module 3 why we are interested in Boolean functions. We will be representing transition systems as Boolean functions. And then for representing Boolean functions, we will use reduced BDDs. So this ends the introduction to BDDs. You should be able to construct a binary decision tree from a truth table and then apply the reduction rules to get a reduced BDD. If you know this, you can jump to the next module.